We are going to tackle the project Euler problems in Rust today. I did the first 50 of these a long time ago in C++. Let's see. February 2011. It's now October 2022, so this is 11 years ago, 11 and a half years ago. And I haven't really looked at them since. Every now and then I get all excited and think I'm going to do them in some other technology. But number one, JavaScript got as far as React for some reason. Probably thought I would like visualize the algorithm somehow. But didn't get past problem one, it looks like. Let's see, Bazel, which is a build system for C++. Solve, yeah, I don't even see, this looks like maybe I did the first problem, but that's it. And I even tried Rust 4 years ago, it looks like, and got as far as problem 7. But today we are starting over. So let's make a new repository. First, let me move this old one out of the way. I won't delete it just yet. Although I don't expect to look at it. Let's see, how do you rename one of these things? Delete, rename. Rename, all right up there. Old Rust Euler, rename. Done, cool. Let's make a new repo. New repository, Rust Euler. Tackling the project Euler.net, is that what it is? Yeah. Problems in Rust. Make it public. What should our license be? MIT. This is now officially going to be an MIT licensed project. Okay. Let's see. So we're going to clone this. Open a terminal. Okay, Rust Euler. Hey, look at that. It's an MIT license. All right. So commit. So let's add a README too, actually. Rust Euler. Work in progress. As attempt the project Euler.net problems in Rust. Just marked down. Let's make this a hyperlink. Just amend the initial commit. Yes, force. All right, let's check this out. LGTM. All right, actually, let's cargo init this thing too. Cargo init. Cool. Let's see. All right, everything's happy so far. Cargo init. Just for grins. And yeah, we've got the lock file too now. Okay, source. I'm going to do these, I think I'm going to do them all as separate programs. So I'm going to make a bin directory. Main.rs will become bin, I'll solve one. Should we call them solve? Euler? Call it Euler 1. Yeah, Euler 1, fine. .rs. All right, right on. I run this. Cool. Hello, world. So what are the, okay, we're done with GitHub for now. What are, or at least done with their web interface. Multiples of 3 or 5. If we list all the natural numbers below, this is going to hurt my eyes. Let's, thank you, Dark Reader. If we list all the natural numbers below 10 that are multiples of 3 or 5, we get 3, 5, 6, and 9. The sum of these multiples is 23. If find the sum of all the multiples of 3 or 5 below 1,000. Okay, so this is basically FizzBuzz. This is a common thing people seem to do, where they take FizzBuzz, which is a well-known, just can you write code? Like, can you write a for loop? Can you make a print statement type of program? And they do just enough of a twist that you couldn't literally paste a solution from somewhere else, which will make it really embarrassing if I can't figure this one out. All right. Might have to rethink some life decisions. Where is this? This is... Actually, you know what we'll do? I'll just copy these into... I'll copy these into comments in the code. Yeah. There we go. I'll make this nice and big so that you can see what's going on. And in fact, let's also do watch cargo check. Cargo color equals always run -- bin Euler 1. Cool, hello world. Let's make this quiet too. Does that go before the run or after? Yeah, there we go, good. All right, cool. So 3, 5, 6, and 9. The sum of these is 23. Find the sum of all multiples of 3 or 5 below 1,000. Cool. Let mut sum equals 0 for, let's say I, in 1. We'll start with 1 because, because 0, it's not going to make any difference anyway. It's an additive identity. Below 1,000. Cool. 1, 2, 1,000. Right on. And we're going to say sum. Oh, actually, let's do this as a filter. We're going to say 1 to 1,000 dot filter some number n. We only want the ones that are divisible by 3. Oops, too much JavaScript. Triple equals. Or divisible by 5. Dot sum. And we'll say let sum equals that. There we go. Now we don't need any mutation or any explicit looping. Cool. And let's try printing that. Print line sum. Why doesn't like that? Oh, it doesn't know what type it wants to be. Let's deal with U64, because why not? Cool. 233168. Is this in fact the answer? Yeah, right on. Cool. The answer you gave to problem 1 is correct. All right, so let's just add a test as we go for these things, so that if we make any changes later, we'll know whether we broke it. Oops. Config. This is probably overkill for something this small, but I know this is kind of the standard layout in Rust. Use superstar. I'll say, here's a test. Function. Test. What's main? Oh yeah, okay, so let's make this a function and we'll have main do the side effects. This is probably better code anyway. Again, not that it particularly matters for this tiny example, but it'll be nice to have a pattern that scales. So we'll say, should we call it by the function name, Euler 1? We'll call it Euler 1. And this becomes that. This returns a U64. Then we don't need this variable or the type hint there because it's on the function. And we'll say print line. Euler 1. And we'll say test. We'll say assert equals Euler 1. And what was the value? Uh-oh. I have to run this again. There's this 233168. Cool. Let's do cargo test. Excellent. All right. And we're on our way. Solve Euler. Solve problem 1. Maybe we should call these things solve instead of Euler. Yeah, we'll see. This will be fine for now. In the unlikely event anyone ever installs this, they probably want to type Euler, not solve. Okay, now how do I get to the next one? Hope you enjoyed solving this problem. Please do not deprive others of going through this by pushing your... Oh, whoops. Don't publish your result. So what do we do? How do you avoid publishing it? You know what? I believe I am not going to deprive anybody of the pleasure of solving these on their own, because I don't think that knowing there's an answer out there is going to ruin it. Plus, the answers are out there. Fact, people have published them. So I'm going to not worry too much about this. Oh, members found to be spoiling problems beyond the first 100 problems will have their accounts locked. Yeah, okay, maybe past the first 100. But even then, that seems draconian. Thread 1 on our private. Yeah, saying just don't tell anybody. Everybody, shh. It's not a movie where a spoiler's going to destroy the movie for you. This isn't The Sixth Sense. But anyway. Okay, so how do I get to the next problem? Problem equals 1. This problem equals 2. There we go. Each new term in the Fibonacci sequence is generated by adding the previous 2 terms. By starting with 1 and 2, the first 10 terms. By considering the terms in the Fibonacci sequence whose values do not exceed 4 million, find the sum of the even-valued terms. I just recently wrote a blog post relevant to the Fibonacci sequence. Oh yeah, we're going to copy these into the code, right? We decided as comments. Then Euler 2.rs. It doesn't like that, huh? Our expected item after dot comment. Oh yeah, fine, because it's not a Rust program yet. Yeah, right on. Okay. Whose values do not exceed 4 million. All right. There's a used iter successors function, I believe. Yeah, cool. Oh, that's interesting. It doesn't want a blank line. Cargo format doesn't want a blank line after the dot comment before the use. It's weird. It makes it look like this comment applies to the import, even though it applies to the... Oh, because it does. I did it wrong. Thank you, cargo format. Is it like that? That seems to make it happier. Let's fix the first one, too. Yeah, these should be bangs, not triple slashes. And nobody saw that. I'm going to amend. No, edit, and get push-f. Okay. And just to be sure, let's see if that looks right. Cargo doc. Okay, so if we go down into target doc, Euler 1, Euler 2, all right. Okay, so if we look at this in the browser, oh, man, that is bright. Let's see, Euler 1. Oh, here we go. Yeah, there's the thing. Oh, the other one has an indented code block. Let's see if that got formatted right. It did. Très chic. All right, right on. So, where were we? Let's go back to our watch here. Oh yeah, that's doing 1. Let's do 2. Okay. Oh yeah, unused imports. Right on. Source bin Euler 2. So I want successors because successors takes a value and applies a function to it repeatedly. So we can get the Fibonacci's. We're return some iterator whose item type is U64. And this will be successors. What is the signature? Let's see. Does the error message tell us? Cool. An option. Oh, right, because it's an iterator. And it's going to want none to let us know when it's done, even though we know the Fibonacci's go on forever. So this is kind of silly glue code. That's all right. So we're going to start with some, and we need to start with the pair. Do they start? Oh, they start theirs with 1 and 2. Or maybe this is, again, it's like FizzBuzz. Like they wanted to start just a little bit different from how Fibonacci's usually go, just so you can't copy paste a solution. Fine. Some 1, 2 will be our first two elements. And then for each successive element, successor, we're going to take, I'll call them A and B, and we're going to return A plus B, B. Okay, expected enum. Oh yeah, because it has to be wrapped in an option. There probably ought to be some Rust library that just for iterators that go on forever to get you out of all all the option glue code, the wrapper types. Expected integer, found ref integer. Aha! Must get passed by reference. Let's destructure them there. Expected tuple found U64. Oh, right. So we don't actually want the pairs. We want to map them to the first element, it looks like. So A, it doesn't matter what the other one is. A, we only want those. Cool. Dead code. Right on. So now, Euler 2. We want the values that do not, terms in the Fibonacci sequence. Okay, so we're going to do Fibonacci's to get the Fibonacci numbers. Does it take while? Argument is missing. Yeah, it's take while. This presumably takes the element, which I will call n here. We'll say n do not exceed 4 million. So that's less than or equal to 4, 3, 4, 5, 6. Expected reference found integer. Oh, again, because this is passed by reference, even though U is copy, the built-in integer types are bitwise copyable. It's passing them by reference just so that it can have the same shape of signature, regardless of whether the types you're generating are copyable. Found opaque type. Expected unit found struct take while. Oh, because this thing doesn't have a return type. And we want this to output a U64. Should be fine. Okay, found struct take while. Yeah, right on. So these need to be summed, right? This is how they're getting out of making you enter gigantic sequences of integers. Just enter the sum. Advent of code does that a lot too. It's kind of a nice trick. Fibonacci's is never used. Well, because Euler 2 is never used. Well, that's a little misleading, isn't it? You should just say Euler 2 is never used. So we will say print line Euler 2. Oh, that can't be right. Take while. Oh, because I have these backwards. This should be B, and then A plus B. There we go. That looks more like a number. It's 2331668. I want to find a way to not be copying the pipe from Tmux there. I suppose I could put those on the left and put the code on the right. Nope. Go back to problem 2. Do not pass go. Do not collect $200. Well, considering the term, let's read this again. Also let me update this a little bit. Each new term in the Fibonacci sequence is generated by adding the previous two terms. By starting with 1 and 2, the first 10 terms will be. By considering the terms of the Fibonacci sequence whose values do not exceed 4 million, find the sum of the even-valued terms. Okay, so we want to... Let's do the filter before the take while. It's always nice to do to perform steps that that remove values before the ones that analyze the values, so you're not wasting time analyzing values you're going to throw away anyway. So we want n%2 equals 0. Okay. That's the same value that we saw, right? Is that... Oh, wait. In terms of the Fibonacci sequence whose values do not exceed 4 million, find the sum of the even valued terms. So that is kind of interesting. Why is that not working? Why is it not making any difference if I filter? 1, 2, 3. So let's take a look. Let's start. Let's debug a little bit instead of this. Oh, and that made no difference because I'm running Euler 1 is why. This is the downside to doing the programming online instead of sharing it, instead of pair programming. You waste time on stuff like, hey, you're running the wrong program. Okay. Oh, you must wait 24 seconds. How are we doing now? All right, check. Ah, shit. Now do I have to wait again because I put that pipe in? Yeah, how are we going to do this? I need a... What am I going to do? I wonder if there's a way to make watch output a space for, like a column indent. One column early. Yeah, probably there is. That's okay. 25 seconds. There we go. Delete the pipe. Check. Ta-da! Okay, cool. I am again. Oh, let's add a test. Other two. Config. Where did we put in the first one? We put it under. We put it after main. I actually don't like having test after main. It's really testing. Let's do this. Let's say test R1 cargo test. Yeah, Euler 2 is broken. Dash dash bin Euler 1. Fine. Okay. Yeah, I'm gonna amend that too. Dash, yeah, same thing. Okay. Source bin Euler 2. By the way, once this is up, I will no longer just amend commits. I mean, once this video is up and anybody is aware of this repository that we just made, I will no longer just amend commits. So I won't screw you up if you fork it and base anything on top of these commits. But as of right now, I just made the repo and nobody has seen this video, so I don't feel too bad force pushing amended commits to master. Sorry, to the main branch. Okay. So Euler 2, also let's put the tests above main, and we'll keep main at the bottom. It's nice to be able to jump to the bottom and see the high-level story, or read from the top down and not have any forward references. So I don't want the tests to come after main. All right, so on test is whatever we got there. And test, function test, Euler 2. We will say, and actually let's make one for just that separate Fibonacci's function, just for grins. Just Fibonacci's. We'll say let, I don't know, vec. Let's call it first. Let's call it first 10. We'll take the first. Oh yeah, it gave us the first 10, so we can use that as a test case. So for the first 10 equals Fibonacci's dot take 10, I think. Let's do this. Go to. And let's put this in the watch command again, actually. Watch test. Run test. There we go. Unexpected token. Fine. Add a semicolon. Take 10. Dot collect. Let's make this a vector. Sorry. 28 vec of whatever they are. We know they're U64s. Cool. Oh, config test. Fine. First 10. This is intentional. No. So now we will assert equal first 10. And it should be this stuff, right? It should be these. Will that work? Yeah, okay. Oh, no color. We need just color equals always. Does that do it? Nope. Maybe it needs to come after. Cargo test is very odd with how you have to pass flags to get it to be in color. Equals always. Maybe it is in color. It just doesn't do it when it's passing. What if we screw this up? Oh, it is in color. All right, fine. Is it in color without this? Is that unnecessary? It is. Sorry about that. It is confusing, though. All right, where was I? Oh, yeah, so I think if we do, I used to like to put the invariant value in a test on the left. Yeah, and you see that doesn't work here. So there's a bizarreness in Rust where you can take a vector and compare it to a slice, but you can't compare a slice to a vector for quality. So for this reason and this reason alone, I have started putting the value I got rather than the value I want on the left. If like me, you grew up with, or not grew up with, if you learned C in college, basically, or if you learned C at a young age, you were taught often to put the invariant on the left, so that if you had, a single equals, you wouldn't silently think that that was a comparison when it was actually an assignment. So you couldn't assign to a literal value, so you'd always put the L value on the left. But it's kind of silly advice anyway, because by the time you know enough to do that, you will also have broken the habit of using single equals for comparison. So, if you're wondering, that's why I have the got value on the left and the want value on the right, which is also, I think, the convention in Go now. I think this is kind of becoming what people expect to see when they read code. All right, so what did we say for the first one? Solve problem 1. Oh, I don't have an initial commit anymore. Whoops, this is why we don't amend, folks. Let's see. Ref log. I'll make this history a little bit nicer. Get reset to this one. Oh, no, actually, I'm happy with doing it after the cargo init. So what I'm doing is I'm moving my main branch back to 3 changes ago. So now, yeah, the whole bin directory is not there anymore. I've deleted source main, right, because that had source main on it. So I'm going to add source bin Euler 1.rs. And I'll go ahead and formally remove source main. Okay, solve project Euler problem 1. You know what, actually, before we do that, should initial commit just say initial commit, or should we give it some more detail than that? That's fine, we'll do this for now. Okay, solve problem 1. You just have to know from context. Oh, actually, it calls them challenges, right? Are they challenges? The answer you gave to problem 2. No, they're problems. All right, cool. Okay, solve problem 2. Very good. Force push. I am going to stop doing that, though, because it's getting already tough to juggle after 2 commits in, 2 problems in. There's got to be an arrow here to go to problem 3, or return to the problems page. So we're supposed to bounce through this. Oh, maybe so you get a chance to admire your check mark. Okay, largest prime factor. Now we're getting somewhere. The prime factors of some number are some numbers. What is the largest prime factor of the number? Some big number. Okay. What is the largest prime factor? All right, so let's make a silly little prime factorizer. Source. You know what I'm going to do? So that we don't have to type so much boilerplate, I'm going to grab one of these things. I'll take the first one, Euler1.rs. And I'm going to put it in my... I have a var directory in my home directory where I put variable stuff, meaning basically stuff I don't want to version. And I'm just going to make this. Oh, actually, even better, I'll make a var directory here. And I think I have in my global git excludes file. Yeah, I ignore var directories regardless. This is very nice. It's a shame that everybody doesn't just stick with a single convention like var. Target has become very common, including for Rust. But it's not just for target stuff, meaning output, things you produce. It's any variable data. This was always part of the file system hierarchy standard. That's why there's a /var on essentially every Unix system. It seems like we forgot that at some point, but it's a very useful convention. All right, so in var, I'm going to put source bin Euler1. Put that in var. We're going to call this, I'll call it Euler.rs. And in here, yeah, that's all right. We'll put this, we'll just leave a little blank thing. Call this, I'm going to start calling these solve. Just so that I don't have to give it a different name every time. Should we? No, because it might become library code, conceivably. All right, fine. So it'll just be called Euler for now, and I'll have to update it. To-do! We'll need a... Let's see, Euler. And we'll say, to-do! Can we get away with that? Let's see. We don't say. Oh, because it doesn't care about that yet. Fine. So print line, Euler. All right, right on. So this is a placeholder. So now, if I copy var Euler to source bin Euler3.rs, since that's the one we're working on. Yep, cool. Now we get some issues. Any code following this expression is unreachable. Yeah, because yeah. Fair enough. Instead of test, let's run Euler3. This is a great example where test-driven development really doesn't apply very well. Test-driven development is frankly badly overrated and can be actively harmful. And one example here is if you imagine you tried to do this test-driven, you'd have to write something to scrape Project Euler as a service to tell you whether you had gotten the right answer. It would be asinine. You're often much better off. I mean, frankly, fumbling around, but it's working bottom up and exploring the space as you go. When you start the project, that's the least you're ever going to know about it. This idea that you have some kind of complete specification that you should be writing to is fantasy almost all of the time. So you're better off keeping your feet on the ground, getting some dirt on your hands before, I think, you start writing tests. Unless you have some really clear case where you know exactly what the test should be. Yeah, not yet implemented. Fine. Sorry, I probably should stop moralizing too. Okay, Euler 3. Let's put in here our problem statement. This is also a nice way to highlight kind of just how silly, or just the idea that a lot of things like user stories or user journeys are not always applicable to everything. And it's like, you can imagine you had to write this as a mathematician, as an aficionado of arithmetic, I want the largest prime factor of the number yada yada so that I can pass Project Euler. It'd just be asinine. Okay, so the prime factors of are, yeah. Okay. Oh, right. Okay, so this is going to become Euler 3. So in here, I'm just going to take all the Eulers and make them Euler 3. Good, done. So this is no longer to do. How do we prime factor a number? So let's say, yeah, let's break this down into, we'll have a prime factors. Prime factor. It's kind of get prime factors, but I don't want to call it get. We'll do this functional. It'll be purely functional anyway. So prime factors, not meaning that it won't mutate anything internally, but just meaning that this, I want this to be expression oriented. I want to be able to, in fact, let's do that. Let's write the higher level code first. So we're going to do. So the signature of this thing is going to be that I want it to return, an iterator? Do we have an iterator over the prime factors? Boy, that would be getting fancy with it. That would be getting fancy. But let's just do a vector for now. And we'll use U64s again. Okay. Here. So now we need, so what we're going to say in here is we'll say let factors equal prime factors of, what's our number, 600 something or other. Thank you, Vim. So what I mean is this is, so prime factors of, this reads nicely as an expression. So that's why I'm naming it prime factors. I don't want to call it a verb because I'm not thinking procedurally. This isn't go do something. This is, I want this property, this value. All right, expected expression. They're going to save it. Argument expected. Argument unexpected, yeah, because it doesn't take one. Right, this needs to take a number. I'll just call this n for now. Fine. Implicitly returns yada yada, as its body has no tail. Yeah, good. So we want the largest one. So we will say factors. There's a dot last, right? Oh, but it's going to return an option. What if something has no prime factors? For example, what if we were trying to prime factor 1? Well, this is fine because it can just return an empty. Here we know that we are not passing 1. So we are going to, I found option. We're going to expect value should have at least one prime factor. Okay, fine. Format, good. Expected U64. Found ref U64. Oh, because last gives you that. I wonder if there's a version of last that gives it to you. Do this. And we really don't need this to be a variable anymore. Let's just do this. We'll say prime factors. There we go. N is unused. Yeah, because we didn't implement this yet. All right, cool. Let's implement this. Actually, let's add a test case now for prime factors. So this is a case where I think it makes sense. It's fine in the middle of your coding to go and start adding some tests. I will, in fact, call this underscore just to shut that up. So we're going to have test, that's the one to test Euler 3. Euler 3, yay. And that's going to fail if we say test it. We want to test it. Yeah, and this is, I'm just going to comment that out. There we go. And I don't want all this noise about the other ones. Is it dash dash bin? Euler 3? Running 2 tests. Because I have quiet on there. Let's get rid of that. Oh, because this also says to do. Okay, good. So we're going to say prime factors of 1. Well, no, 1 we will get an empty vector. So again, I can do the slice there. Cool. Haha, you see that, how the order is flipping of these tests? So as you let this go, if I write that, it can be, there, the order just changed, and it's gratuitously. It's because cargo test is probably running these tests in multiple separate threads. Or even sub-processes, I don't know how it works. but there's a race condition where you don't get consistent output. Boy, that's annoying. So we're going to tell this we only want single-threaded tests. So cargo test single thread. It's probably num threads or something. Test threads equals 1. All right, cool. Let's try that. Dash dash test threads equals 1. Dash dash bin Euler 3. Did you mean dash dash test? Did I mean dash dash test? What did that say? Cargo test dash dash. I'm telling you, man, these no such subcommand. The cargo test command line interface is not optimal, not ideal. Unrecognized option bin. Oh, that probably has to go before the dash dash. There we go. So now these will be, I think they're in the order we wrote them. This is supposed to be test prime factors. Is that true? Oh, no, it's not. Look at that. It must be alphabetical or like ASCII-betical. Test Euler 3, test prime factors. Huh. That's also counterintuitive, isn't it? All right. So we want to make this the one pass. This is a little bit of a lie that this is passing. I'm just going to make this. I think you can make any kind of config you want on these things. To-do. Yeah, it just doesn't run it. Cool. And I'll say, yeah, good. All right, so prime factors, not yet implemented. Right on. Let's add a couple of other assertions in here. 2 should just be 2. 3 should just be 3. Oh, no, we want, well, yeah, this doesn't even care how many. Said, what is the largest prime factor? It doesn't care what exponent they are raised to. All right, fine. 2. Right? Or we can push them on multiple times. Let's do that. We'll just have them appear multiple times for now. Just because I find it a little unintuitive to not think about the exponent at all. 5 should just be 5. And 6 will be good enough. That has I just want one that has multiple prime factors. Right on. All right. So let's make a mutable vector that will be our factors. Back. New. At the end, we'll return this. And this actually should compile. Remove this mute. Fine. And it just fails. Right. It fails on the first one because 2 needs a factor. Ha! It happens to pass for 1, actually. Ironically. So we're going to have in here for I in start at 2. Actually, let's say let candidate as a potential factor equal 2. Mute. And we'll say while we need n. I'm actually going to let this, we're going to mutate n. While n mod candidate equals. No, actually, we want to go until we've passed. As long as our candidate has not exceeded n. Expected type. Is that not how you do that? Do we need this to be over here? Expected type. No, right? Mute n. U64. Why is that not happy? Cargo check. Remove this mute. Yeah, fine. Yeah, okay, fine. Help a local variable with a similar name exists. Oh, because it's still called that. Why is my watch? Is this cargo test hanging? Let's get rid of the watch part. Oh. It's because it went off into an infinite loop. Because of course it did. Because we have no, we're not doing anything to candidate. Da-ha-da-ha. All right, so at the end of this, we're going to say, while candidate less than or equal to 2, n slash equals candidate, and factors dot push candidate. That. Oh yeah, actually, only if. Okay, so here we go. I just need an inner loop here. So we're going to proceed while the candidate is less than or equal to n, but both things are going to be happening. The candidate's going to grow, and n is going to shrink. So we're going to say, while n mod candidate 0, meaning n is divisible by the candidate, we'll push the candidate into our list of factors, and n slash equals candidate. This is basically a for loop, like a traditional C-style for loop. We'll say, then afterwards, candidate plus equals 1. There we go. Cool. Go back to our watch command. Yeah, look at that. It's not doing, where'd our color go? Just color equals always. There we go. All right, cool. So, we now are able to prime factor numbers. And we want, we already had this part. We wrote this ahead of time. So let's see. Largest prime factor of, yeah, if we really wanted to get fancy, we could try passing in different numbers for Euler 3. But instead, let's just say, yeah, we're going to run it. Let's run it. Cargo run dash dash bin equals Euler 3. 6857. Is it indeed? Was this your card? Yeah, right on. All right, so now we're just going to add a test here. This should be 6857. And this test should no longer be ignored. Okay, cool. Solve, whoops. Oh, because it's not, duh. Solve problem 3. Push. Cool. All right, let's go on to problem 4. I just went for coffee and was reliably informed that ProjectEuler.net has a dark mode, a dark theme. So we're going to use that. I'm going to turn off my extension here. Whew, that is bright. We're going to look at the account. Okay, where is it? Theme, dark, update settings. Okay, now we have their native dark theme. Now where were we? Progress? Oh, okay, 4. All right, let's do this. I have just copy var Euler to source bin Euler4.rs. Change all of the Eulers to Euler 4. Cool. A palindromic number reads the same both ways. Largest palindrome made from the product of two two-digit numbers is 9009, which is 91 times 99. Okay. Find the largest palindrome made from the product of two three-digit numbers. Yeah, okay. So we're going to go through, so this is like order of a million, right? We're going to do all the three-digit numbers times all the three-digit numbers. Filter out the ones that aren't palindromes and take the last one. Or better yet, let's go from the top down, starting from 999, and we'll take the first one. All right. So we'll say, let me get this thing running. Watch. Run. Great. This will be threads equal. No, I want that to be Euler 4. Okay. Okay. for, and we'll just bail early. Yeah, in fact, we don't even need to do anything fancy. We can just bail out of a nested for loop. For, can I do a range counting down? What I want is for, say, I in 999, 3-digit numbers, presumably not beginning with a leading 0, down to 100. Down to 99, we'll say, so it includes 100. I'm just going to say to do here for now. Does that work? Yeah. If I'm just going to say, see if we hit 100 at some point. Return 100. And otherwise, if we get to the bottom of this loop, we're going to return 0. So if I run this, 0. So apparently I cannot just count down like that. Let's see, Rust loop through, backwards. Yeah, of course, you'll just reverse it. So that's what we're going to do. We're going to take 100 equals 99 dot rev. There we go. And now we're hitting this loop. Our loop is looping. To do. So we'll say, we need the same thing now for an inner loop, j. We'll say if I times j is a palindrome. I'll have to write this in a minute. Return the palindrome, right? I times j. So we'll say I times j is palindrome n, return n. And at the bottom, what if we don't find anything? We could panic. So we believe this will never, ever fail. Should we return a result anyway? Yeah, I'm going to do, there's no way to do an expect here, huh? This would be one nice thing about doing it functionally is if we had an iterator, we could use a method that returned an option, and then we could call it .expect on it. That's okay. Panic. No pair of 3-digit numbers has a palindromic product. Okay, cool. Well, let's just say that. So function is palindrome. N will be 64. This is a good one to have a... Or did we test 3? Source in Euler 3. Yeah, we did. Good. Okay, so we can add a test for this one too. We'll say test is palindrome. Just because we know, let's say, let's do assert is palindrome 0, I suppose. Cool. Why am I putting that in? Because I think of palindromes as strings is why. And we'll, 1, say for I in 0 through 9. Assert is palindrome I. Fine. And we'll say assert is palindrome. Assert not is palindrome 10. Assert is palindrome 11. Assert not is palindrome 12. Let's just do a few big ones just for grins. Assert is palindrome. We're going to have up to a 6-digit number here, huh? Because it's a product of 2 3-digit numbers. Say 1, 2, 3. Actually, let me make it something else in the middle. 9, 8, 7, 7, 8, 9. There we go. and not is palindrome. Change one of the digits. Actually, I'll change one in the middle. Make that a 6. Cool. It's palindrome. Bool found. Yeah, good. Fine. It's. So if I just say false here. Well, first of all, this thing needs to return a bool. Help if it's intentional. And yeah, good. Fails the test. So we're going to say, do we want to get fancier or do we want to just convert it to a string? Because what we care about is really the base 10 representation. Yeah, let's just convert it to a string. I know it's lazy, but it's fine for this purpose. I'm going to say format n. That will give us the base 10 string, the sequence of digits. Let digits equals format. Good. And we'll say I 0 dot dot equals digits.len, the number of digits, or 2, because we're going to have to scroll through the first half and compare with some, for each of them correspond with, check against some corresponding digit, counting back from the end. So we will say, is it all? This is the Rust standard library documentation. So we're going to say iterator. All, yeah. Takes a function, cool. Dot all. Here's the index. Say digits at I equals. Oh, we can't say digits at I. Dot chars. Ooh, gosh. I want something we can index. So let's make this a vector. Make this a vector of, it'll be a vector of char. We'll say format dot chars dot collect. It's at I, digits at n minus I minus 1, right? Because n minus 0 would be past the end. Expected U64 found U size. Expected U64 found U size. Because n is a U64, and I can't use that as an index. As U size. Oh, I don't want n anyway. That's being silly. I want, thank you, type system. I want digits.len. ISI. There we go. Cool. I don't like that. 580085. They want the palindrome. Is this correct? 580085. Nope. All right. Oh, because it's possible that because I'm not going through them in order of the product. I'm going through them in order of I major, like row major order. So, what are we going to do? We want the largest product. Yeah, so I'm just going to keep a mutable variable as like a cache of the last one we've seen. And then whatever the last one we saw is, that's the answer. Let mute result equals, I'm just going to start this at 0. And at the end, we're going to return results. If I were really feeling rusty, if I were being hardcore, then I would use an out of band type here. I'd use a monad like an option. but I'm going to not do that. It's just going to be an integer. So, so I might as well now go in any order. It doesn't matter, so we can get rid of these reverses. Because I'm going to go through all million. I know this is naive. If is palindrome n, and n is greater than our existing result, then result equals n. I know 6609. I wonder if it's worth using is palindrome and then n greater result dot then result equals n. That's not better, right? That's worse. All right, here. Okay, so I know 6609. 906609. Bada bing, bada boom. All right, let's add a little test. This is going to test Euler 4, if not our patience. We'll say assert equals Euler 4. I know 6609. So if we test this, cargo test, and Euler 4. Cool. Looking good. Oops, edit. Solve problem 4. Push. All right. Let's go over to 5 here. Let's change the URL. 2520 is the, look at this. Look at their dark mode. It's no better than when I had dark reader on. You see what they did here? They just inverted the colors. So the shadow looks like a glow. That's not how you do dark mode, folks. I mean, nothing but love for Project Euler, but that's if you're ever writing a dark mode, shadows are dark even in dark mode. They shouldn't be a glow. You can't just invert the colors and think that's dark mode. Anyway, 2520 is the smallest number that can be divided by each of the numbers from 1 to 10 without any remainder. Okay, good. Yeah, it's the least common multiple. What is the smallest positive number that is evenly divisible by all the numbers from 1 to 20? Yeah, we want the least common multiple of the numbers from 1 to 20. All right. Copy our boilerplate over here. Short spin Euler 5.rs. Euler 5. And we're going to add doc string here. If I can type. I wonder why it wants to indent that. 2520 is the smallest number that can be divided by each of the numbers from 1 to 10 without any remainder. What is the smallest positive number that is evenly divisible by all the numbers from 1 to 20? Cool. So we need function LCM. Returns the least common multiple. It's always going to be from 1, huh? Isn't it? LCM 2. Gee, that's a little confusing. N. What do we call it? LCM beneath. I'm just going to call it 2, and this is going to be exclusive. So it's going to be the least common multiple of all natural numbers strictly less than n. And this is where, how do the doc tests work in Rust? Basic idea is triple backtick start and end code blocks. Yeah, fine, good. Rust doc dash dash test. Extract this example and run it as a test. Really, then you have to run rust doc to run the test? Is there not something that can pass to cargo test? Cargo test. Oh, there we go. Dash dash doc. Okay, so we can say, do I need it to be an examples section? Really, with a level 1 header? That seems extreme. It'd be nice if they showed more complete examples. Examples. All right, apparently that's the convention. Examples. And we'll say, we need a code block. LCM2. What's the least common multiple of the numbers to 0? It's 1, right? 0 is divisible by 1. Search. 2. This is going to be just redundant with our test, right? That's okay. 2. Whoa. Very unhappy. Yeah, again, let's just ignore this for now. Ignore me. These super unused imports. Yeah. You know what? Let's just... Goodbye, tests. It's intentional. Yes, it's intentional. Dead code. Fine. What about dash dash doc? Can't mix dash dash doc with other target selecting options. Really? I can't do the doc test just for Euler 5? No library targets found. Oh, it only works with libraries, huh? Well, it was worth a shot. So down here, we might as well just have a test. Function test LCM2. We'll say this is a test. We'll say there we go. Okay. Failed. Why is it failing? Yeah, because we haven't implemented it. Cool. So we will say, how do you compute a least common multiple efficiently? I suppose what you do is you prime factor all of the numbers involved, the entire set, and you take the highest power of each prime factor, and that's the multiple. That's the term you need in a final product. Yeah, this is actually going to be a bit of a bear. That's okay. We'll get it done. So we need, in fact, let's just say we need LCM of some numbers. Numbers. These should be, I don't want to call them naturals because I want to accept 0 just because 0 is in band for the U64 type, and I don't want to start getting fancier with the types involved. LCM. I have some numbers. And they will be some iterable of U64. And this will return a U64. Look at that, still no color, huh? Why no color now? Because cargo also needs it? Yeah, okay. 64, good. So I want a better prime factoring function. So here's another interesting kind of design question. Do we leave the ones we already wrote alone? Because we needed prime factoring in the previous exercise. Or do we now factor out or write a, factor out, no pun, do we now write a library function that does prime factorization and update the old code to now call the new library function? I think it makes sense to go that way rather than to have potentially redundant code in multiple places where bugs could exist. But I could see a case either way. So let's say here, what we're going to end up doing. Let me put a to-do in here for now. I don't want to get, before we fall far down the rabbit hole. We've already got 3 to-dos here. Euler 5 is going to be, it's the smallest positive number that's, okay, so we're going to need LCM 2. This basically is. In fact, we don't really need this function at all. Yeah, that is Euler 5. So we're going to say LCM returns the least common multiple of specified numbers. Good enough. Sure, LCM of, let me just make this thing Lex. LCM, we'll say, of no numbers is 1. Let me make this thing pass. So we'll say LCM of, and it's going to be from 1, so the 1's irrelevant, up to, and including 20, because there 2 means inclusive. Mathematicians seem to like inclusive ranges, even though programmers tend to prefer half-open ranges for good reasons. Oh, no semicolon. Cool. This is going to panic, so we're going to say failed. Yeah. Oh, so what we can actually do is we'll loop through all of the numbers, the specified numbers, and for each of their prime factors, prime factor pairs, basically a prime factor raised to a power, each term, we will ensure, it might make sense, in fact, to store our number as a mapping whose keys are prime numbers and whose values are the exponents to which those numbers are raised. And at the end, we'll compute the number. So then we'll roll through input numbers, roll through their input factors, and then just make sure the value in our map is at least as high as the value of the exponent for each of these terms in the prime factorings. Let's do that. At least I believe it will work. So we're going to need a map of some type. State collections hash map. We'll say I like to name maps, dictionary types, after the value, because usually in the code where you see them used at the call site, you see the key. You know that that's a key, and you want to know what that key refers to. So it's nice if the map tells you what the values are, what they represent. So we'll say, I'm going to say powers. Hash map, new. In fact, I'm just going to specify a type signature here for now. We'll map each factor to exponent. Maps primes to exponents. factors, 2 exponents. And at the end of this, we'll need to compute the actual number. So we'll say, let's call this a power map, actually. Type, power map. Should we make it a struct? Because we're going to need a function to work on it. It could have some methods. Not yet. We'll make it a struct later, maybe. I don't like the idea of calling it map and then not having it be a map if it just wraps a map. What's a word for a set of prime factors and exponents? This is going to be all right. I don't like calling it map and then not giving it an index operation. So let's just make it a type for now. Power is going to be equal to this power map. I expected U64. Yeah, will Russ let me do this? Can I say power map equal? You can do this in C++, I know. Yeah, all right, cool, right on. So we have a power map now. We're going to say at the end of this, 2 or as? I think it's just 2. 2 value. 2 U64. I'm going to call it to value. Powers. So we'll need the to value function. Yeah, this is why Rust really wants this to be a method, is because there's no overloading like in C++. So if we wanted 2 value functions for a bunch of different types, they'd all have to have different names. All right, power map. The hell with it. And I apologize for the fact that this is called a map and it actually merely wraps a map. If you have a better idea, leave a comment. Map. So let's call this powers is A. Right, it's one of these things. Represents a number by storing its prime factors and the powers, exponents to which they are raised, and their powers, exponents. Represents a number by storing it. Stores the prime factors of a number paired with their exponents. There we go. That'll do. Now I don't really need this comment. So this becomes impl power map. We have to value, takes ref self, returns a U64. To-do. Cool. This becomes power map new. Oh, he needs a new. Although if it's just in here, this is eventually, I'm sure, going to get moved to library code. It seems like Euler, Project Euler likes primes a lot. Do we want to give it a new method? Or do we just want to say, yeah, all right, we'll give it a new method. So we're going to say function new returns self, and power map powers is hash map new. Okay, to value, yeah, because this is now powers dot to value. Field in the struct, warn dead code. Yeah. I wonder if it's worth. There must be a flag you can pass to cargo check or build or run to cargo commands that means allowed code. I know you can do it as an annotation, as an attribute in the Rust code. But I don't want to be adding. I tend to forget to remove them. I don't want the, and it changes line numbers and things. I just don't want the detritus in the code. So that's all right. We will implement this first, and then that'll go away. So we're going to say that mute value, since we call this to-value, equals 1, because that's the multiplicative identity. We're going to say for factor power in self.powers. Can I do that? Is that how that works? I think so. I always get this wrong. I forget what you get when you iterate over dictionary types and over map types, and I get bitten by it all the time in languages like Python or JavaScript. And I really appreciate that in Rust, the type system will tell me if this thing isn't returning a pair, if I'm doing it wrong. So we want, yep. Is there exponentiation? We don't have an exponentiation operator. Rust x power. Electricity in Rust get charged. That was a rough search. Raise number to power. Is it just math.power or something? Base.pow. Oh, cool. It's a method on the numbers. Right on. So we're going to say factor.pow power, say value times equals. Excellent. Oh, it wants a U32 specifically because we can't raise things to U64s. All right, our powers will be U32s. Powers moved. Move occurs. Because this does into iterator, huh? What if we do it by reference? Yeah, so now let's break those down. Iterator with items of type yada yada. Expected tuple found reference. Why does that work in a lambda when you're destructuring the arguments, but it doesn't work in the loop? Fine, we'll destructure them separately. Value times equals. Factor.pow power. Good. I'm not going to add tests for that yet because it would be more of a pain than I think it's worth. Powers to value. So now we want for number in numbers. Help a local variable. Yeah. Okay, so now it's used. All right. Just can't make Rust happy. For a number of numbers, we need a set of the prime factors and their powers, which actually can now return a power map. Maybe it should be like a power list, and it should actually be iterable. That's probably the way to go, in fact. Yeah, we could get fancy. I don't know. You want to get fancy or not? Numbers. I think we do. And we're going to have a merge operation. So power map is not going to be a power map. It's going to be a power list paired with their exponents. So this is going to be, oh no, because we want to be able to look up the exponents directly. So fine, this will be a power map. And it will be, when we factor a number, so we're going to have prime factor. Didn't we call this prime factors, though, in the other one, in the other routine? In 4, right? No, 3. Yeah, prime factors. Yeah, because we wanted the prime factors. And it didn't return the pairs. Prime factor. I'm going to call it prime factor anyway. I'm going to say, and this will return a power map for a given number, n. which is a U64. Okay. Yeah, it's intentional. Four number of numbers. We should probably get consistent too with n versus number. I'm going to say for n in numbers. This is intentional. Prime factor, good. So for n in numbers, power map. We'll say powers dot merge maybe. This is a bit of a weird operation. It's not just multiply all of the powers. I'm going to call it merge for now. Dot merge prime factor. Oh, we can call it, instead of prime factor, actually, let's just make this a static method on power map. Function power map for value. Yeah, we'll take the value, U64, and then it gets called value. And this will return a power map. Yeah. This is going to be the opposite of toValue. So maybe there is no new. A new power map would be the power map for value 0 or 1. It would just be 1. Yeah, we'll come back to that. So this will be powers.merge. Let's say merge value. I'll have a merge value. N. So within power map lingo, a value is what we're calling the number. For value. Yeah, because it needs to return a value. All right, so we're going to say let powers, let mute powers equal hash map new. And at the end of this, we're going to return a power map with those powers. Method not found. Cool. Oh, do we even need one for value? I bet we're going to end up needing that again eventually. Yeah, okay, so we're going to skip that for now. We don't need that function right now. It's going to be merge. And this one we'll take self, mute self. Merge value. So now we don't need this. We'll say we need to do the prime factoring. I'm going to copy this logic that we had from number 3 here. Yeah, that's always a sign you should probably be refactoring something. Factors back new. Well, now we don't need this because that's in self. The mute candidate equal to. Well, candidate is less than or equal to. I'm going to call this n again. N. Candidate less than or equal to n. N on candidate is 0. Factors.push. So instead of factors.push, okay, we're going to say let power equal 0. Anything, any number is divisible by any other number that's raised to the 0. So that's fine. So while n mod candidate equals 0, power plus equals 1, and n slash equals candidate. Good. So after that, if power is greater than 0, now we have to merge that. So we will say self.merge power, and we'll take that factor and that power. And I'm going to, instead of candidate, I'm going to call this thing factor. Candidate factor. Yeah, okay. Factor power. Merge. Okay. Let's see. Updates this power map such that it includes all of the prime factors of n raised to at least the same powers as in n. Parentheses, in addition to whatever factors and powers this power map already contained. It's a little bit dense. Dot merge power. Probably don't need this to be a separate function. Let's just say, no, because Rust has a whole thing where you have to go, what's it called? It's called, you have to go get the entry. So I want hash map entry, if you want to mutate it. Hash map entry. Okay. Yeah, like that. And modify. Or insert. Yeah, that's exactly what we want. We want, in our case, it's going to be self.powers. I don't need this factors thing anymore. Self.powers dot entry, that factor, dot, if it was there, so and modify power by reference, star power plus equals. Oh, no, we want it to be equals to max of whatever it already was. Oh, is equal power dot max? Yeah, I think it's a method on numbers in Rust, which is nice. Dot max. Oh, this is the old value, though. Old power, star old power equal old power dot max, the new power. Or insert one. No, or insert the new power. Good. Factors help a little. Okay, why is it unhappy? Oh, down here. Yeah, because now we don't return anything. It's a mutating method on self. Okay. Merge power found and not found. Merge power. Nope. Expected. Found integer. Ref mute. Why does it need to be ref mute? Consider borrowing here. Ref mute power. Is it so I can take it? Max. We want U64 max. Oh no, U32, right? U32 max. U16, U32. Let's just look at the docs for the primitive U32 type. U32. Is there a max in there? Max value. Max, there we go. Compares and returns a maximum of 2 values. That looks fine. It looks like exactly what I would have expected. 1.max2 equals. Just trying to take the max of the references. A mute factor. Oh, that's a bug. That's actually nice. So this caught the fact that I forgot to increment this. It told me it didn't need to be mutable, but of course it does need to be mutable. I just forgot to mutate it. It's very nice. Good for Rust. Okay. Well, factors less than or equal to 2. Okay, factor plus equals 1. Power. So let's make this bindable 27. Right, of course. Consider making this binding mutable. Right, because we're going to be decreasing it. Expected type. Didn't we go through this earlier? Mute n. Powers. Consider changing this to be mutable. Mute powers. Yes, it is going to have to be mutable so we can merge these values into it. Prime factor. We no longer need. Oh, we will, though. We sure will need that. Okay. Yeah, that's weird. Oh, so the references will try to take a max? That is also bizarro. Look at that. Well, that's why it wants a reference. Why is there a max method on references? Why does Rust have a max method on references? Reference max. Nope. Max reference. In max, I hate reality. Yep, I don't know. But apparently that's it. Okay. And we need the reference so that we can mutate the original. All right, so were we testing this? What exactly is passing here? Oh, the least common multiple of nothing. Test LCM. Let me change this one to be test Euler 5, since that's what's eventually going to test. Good. Least common multiple of 1 should still be 1. Of 2 should be 2. Why does that work? Oh, because we implemented this. Okay. We should do this with some that are not in order too. Let's see. So 3, 3, 4. Oh, this is just individual values. So that's fine, actually. So let's say 1 and 2. 2. What about 2 and 3? It should be 6, right? Cool. Yeah, all right, right on. Let's get one with 2 factors. Let's say 9. I'll put them out of order too, just to make sure that they're out of order. Let's give it a third value too. Say, I don't know, 25. So what's 25 times 9 times 2? 450. Will that do? Oh no, we want one where they have the same power. So let's make this 18. Right? So that should be the same. And we'll make this 18. So this is a 2 and 2 3s. And we'll make this one a 6, so it has a 2 and a 3. And make this one, 15, let's say. So then we have, this needs a 2 and 2 3s. This needs a 2 and a 3, so that's already covered because 6 divides into 18 evenly. This needs a 2 and a 3. We've got the 3. Sorry, it needs a 3 and a 5. We've got the 3. We need a 5. So this should be 30, right? No, of course not, because 30 is not divisible by 18. Oy vey. All right, 18. Why can't I math today? 18 is 6 times 3, or 2 times 9. It's 2 times 3 times 3. 6 is what? 2 times 3. So this is irrelevant to us. 15 is 3 times 5. Okay, so what we need at the end of this is 2 times 3 times 3 times 5, right? Which is 18 times 5, 50, plus 40 is 90. This should be 90. Oh, and in fact, the Rust test output is telling us that it does pass, or it will pass in a second. It gives us the right value. Okay, cool. So we're making progress here. We have least common multiple. Is that all we needed? Yeah, that's all we needed, right? So I'm not going to update the old exercise to use our power map thing. And we don't need this prime factor function. This is still short enough, small enough that I don't think it's worth factoring out yet. But I get the feeling it will be as these problems get more complicated. All right. So what we want. Oh, that's it. Actually, this should pass now, right? Let's just unignore this. Nope. Oh, to do, because we need to. We don't know what this is. We just need to run it. Cargo run dash dash bin Euler 5. Ooh. That's a number. Okay, cool. So, okay. When tests pass right away, I like to break them just to make sure they're running as I expected. Cool. Oh yeah, it's still doing that thing with the. I want the build to be quiet, not the test. If I do dash dash quiet, does that work? No, it makes the test quiet too. Oh well. Oh, you know what though? I think that works around the threading issue. Maybe if we had multiple failures, that would be an issue. Let's make one of these fail. Okay, and what if this one fails too? That ordering looks consistent to me, even though we're not giving a number of threads. All right, fine, so that'll do. And pass. Solve problem 5. 6. A bunch of instructions. This looks complicated already. Is that not? Is that selecting? Is that an image? What is that? Oof. Math jacks. Really? You could write a very simple equation? Oh, all of these. This might get to be a pain. Let's see what happens. Euler source bin Euler 6.rs. Make this a comment. The sum of the squares of the first 10 natural numbers is. How do I get this as text? Oh, because this is the first one where they needed exponents. And it turns out that Unicode's exponent support is really not very good. That's all right. It's Unicode squared. Probably I should just use some kind of notation, some simple notation. B2, right? 1 squared plus 2 squared plus 10 squared equals 385. One, was it? It was B2. Yeah, so in Vim it's control V, U, B2. 1 squared plus 2 squared plus up to 10 squared. 2. Oh, you know what? There's also a digraph for this. That's right. B2. I kind of prefer to use the Unicode values directly, just because that way it's not only in Vim. There are also ways you can, like Mac OS has you can set a Unicode keyboard so that you can enter the Unicode values directly and everything, whereas the Vim digraphs are basically Vim and Vim only. Plus 10 squared, right? Oops. Equals 385. And then it's going to be the square of the sum instead of the sum of the squares. 85. The square of the sum, 55, right? 385. Cool. Hence the difference between the sum of the squares of the first 10 natural numbers and the square of the sum is 3025 minus 385 equals 2640. Yeah, this is 3025, right? 3025 minus 385 equals whatever that is. I go 3025 minus 385, 2640. All right. This is inline. All right. Find the difference between the sum of the squares of the first 100 natural numbers and the square of the sum. Oh, good. That's not going to be too big. That's 100 factorial, right? That's going to be huge. The sum of the squares, I think we're okay with. The square of the sum. Well, you know, we're fine. It's not the product. It's the, yeah, good. Euler becomes Euler 5. No, sorry, Euler 6. Good. So we have, let's just make some little functions here. I will have sum squares 2. My 2's are going to be exclusive just because I want the half open ranges. And 64 returns the sum of the squares of all natural numbers less than n. You know, we don't even need 2 here. Sum squares. This will be square sum. This is pretty specific to this problem. If it comes up more, maybe we'll rename them, or at least move them to some like module, some namespace. Returns the square of the sum of the of all natural numbers less than n. Good. Squares. All right. So we need 1 to n square the sum. Oh, okay. So Euler wants them to be inclusive. I don't want to say less than or equal to n. Yeah, the heck with it. We're going half open. I think I'm declaring by fiat that our. Feel free to fork it if you hate half open ranges. So we have 1 through n. We're going to map for each of those. It's square I times I dot sum. Start looking at 6 here. Yeah, fine. Square sum. And this one will be dot sum squared. We don't have a squared function. Let sum equals that. Sum times sum. It doesn't know what the type should be. It should be a U64. Really? Adding up a bunch of U64s? You didn't know it was a U64? Euler 6. Good. So we want the difference. So we want the square sum of, what's the number? Find the first 100 natural numbers. Right, including 100. So 100. But 101 because half open. Minus some squares. 100. Good. Let's just run it. Cargo run dash dash bin Euler 6. Oh, there's a number. Okay. Let's put this in our little test. Okay, we're passing. That's Euler 6. Yeah, good. Might have to stop adding the problem statements into the source code, just because it's not going to be worth transcribing the mathematical notation. Solve problem 6. Okay. How's problem 7 looking? Well, this one looks easy enough to copy and paste. Var Euler source bin Euler 7.rs. Euler 7. you can see that the 6th prime is 13. Well, yes, that's true. What is the 10,001st prime number? First prime number. Are they German? Oh, because Euler. Space. Because they didn't do this or that. By listing the first 6 prime numbers, we can see that the 6th number is prime. What is the 10,001st prime number? Oh, they're telling you how to implement it. They're saying go ahead and iterate through them and take the last one. Oh yeah, okay, fine. So now we're gonna need to start computing primes. We probably want a little library of prime code. lib.rs. You know what? We could make the earlier ones more efficient too by instead of just taking our candidates and walking through them. So once we have an iterator because I think we should make an iterator that just generates primes. It's fundamentally an infinite sequence. So for the ones that we have where we prime factor these things, instead of just incrementing our candidate by 1 each time, we can just ignore any candidate values that aren't themselves primes. Because if we've already pulled out all the factors of say 3, then 9 is definitely not going to divide into whatever's left. So it might be worth coming back to these, or not. There's always a tension between whether to make the code that's simplest on its own, or to make the code base that is collectively simplest. So it would stink to add a dependency, to say that this thing now has to call into library code, since it's such a little gem of, not that it's awesome code, but just that it's a standalone polished thing. It kind of comes down to, in your dependency graph, are you willing to introduce dependencies in order to simplify the individual nodes? There's a tension between the weight of the nodes in a graph, if you had sort of weighted nodes, versus the density, the connectedness, how many edges you have. Sorry, that's very abstract to show you without any pictures, but I think we will not have pictures for now. So, source bin Euler 7. Okay, so we'll start with the primes in here, and then I'll probably factor them out to a library and change the earlier code to call it. Or maybe just going forward, use it. Okay, so we need primes. We'll return some iterator. We'll make it, so we'll have primes. That's kind of a Rust convention. I think that we call our iterators, they're not called something iterator. It's not like C++ or Java where you say, oops, that's not what I want. Where you say, I have a prime iterator. It would just be like if I have, I don't know, we saw take while earlier, right? Like, it's not called take while iterator. It's just called take while, map while. So I think we'll just have primes. So primes is going to need, what's the state you need to compute primes? Let's just say we'll have the known primes, right? Known. And that'll be a vector of U64. At some point, too, we might need to change this. This all might need to be generic, where it's not just U64. Or we'll just opt into some big int type. Known? Is that all we need? Is that all we need? Yeah, I think that is. And then to get the next prime, this is going to be n squared. Is it n squared to find the next prime? Oof. Because what we're going to have to do is start with the highest known prime, and then start looking after that, one at a time, or every other one if we special case even numbers, and just flat out check every known prime to see if it divides, or every prime up to its square root. Right, we don't have to go past square roots. Because if something is not divisible by any numbers up to its own square root, then it's certainly not divisible by any numbers past that, except itself. All right, so that's it. So that's all that's going to need. We're going to, let's just give it a new constructor here. Primes. Should we say self? What's the convention on when to say self versus when to iterate the type? What does take while do? Source. Is there not new? New. Create. No, they wrote out the type. All right, so we'll write out the type. Primes. I probably should have done that in the other one too. So, yeah, source bin. Oh, it's the one we, that's 2 ago because we just did 6. All right. Self. Yeah, power map. Okay. Tweak a return type for clarity. Fine. Euler 7. Okay. And known is going to have to be an empty vector. I'll start doing this start building number 7 so we can see all the things we've done wrong. Okay, to do. Yeah. Yeah, I know that. I kind of want it to not warn me about unreachable code. Maybe we should enable can we cargo disable warning on command line? Come on, yeah, here we go. Boy, that is bright. Rust flags equal -a warnings to allow all, but any changes to rust flags causes everything to rebuild. Yeah, fine. Cool. Export rust flags equals -a. Why is it unreachable code? Cool. Now we still got a little bit of dead code. That's okay. No big deal. We want. Oh yeah, we just need the nth. So Euler 7 is just going to be primes new dot nth, and they I think like many mathematicians begin their indexing from 1. Okay. Dot expect primes should be inexhaustible. Is there a largest prime? Is that even known? Do we know whether there's a largest prime? I kind of assume there's not, but not found for because I haven't made an iterator yet. Impl iterator for primes, and we'll need type item equal U64. Missing next. Cool. I love how they give you these little signatures. I much prefer this to like an IDE that tries to fill in the boilerplate. I just want. This is what I want. Okay, good. So self item, which is a U64. Maybe it makes sense to use self in trade impulse, but not in the main impl. Expected enum option found, yada yada. Right, indeed. To do. Dead code for known. Yeah, good. That's fine. So we need to find the next prime. Right, and then we'll get nth for free. We have a failing test. Yeah, noticed. Unused. Failed. Oh yeah, because to do. Okay, cool. So we are going to start known. No, we can start with something. We don't. It's not like we know no prime numbers. So let's start with vec of at least 2. At least 2. Let's see. Yeah. And maybe we special case. I think we're going to need an is prime. So you might need an is prime method. How do we find this? So let's try implementing. We'll outline the algorithm and then see if it's useful. So we're going to say let last equal. No, we're going to candidate prime. This might be a little confusing since we used candidate in an earlier exercise to mean a potential factor. Maybe I should change those to bfactor. Or we could get all mathy and just call it p. Value. Let's call it value. Yeah, p. Fine. P for now. Is equal to self.known dot. Although I don't like the idea that new might allocate. I like the idea of starting as an empty vector. Let's start it off as empty, and then nothing will happen until next. So we'll say if let n equal known dot last, maybe match, if let sum n equal known dot last. There we go. We're going to do our thing. Else self.known. Yeah, this has to be self.known. Dot push 2. And we will return. You know what we're going to do. Here, this will be, we need to find the next one. This is going to give us, oh no, he turned off the unreachable code warnings. Very nice. Sum n. Not found in this scope. Of course it's not. We will say self.known dot last. There we go. Found ref64. Why ref64? Oh, because last is by reference. Dot cloned, is that a thing? How do you deref an option? Deref, or option, let's take a look. I want to turn an optional reference into an optional not reference. Clone, there we go, cloned. Option, yeah, perfect, beautiful. Cloned. I believe iterator has a similar method. Good. Okay. So if it was empty, then it's going to be 2. Otherwise, we're going to take the last one. We're going to say mute. Fine. N plus equals 1. While not self dot is prime n n plus equals 1. But it would be great to skip the even numbers once we get past 2. Yeah, let's start with 2 and 3. So that the last value is always odd. I'll add the comment where we do the plus equals 2. Can I use on type U64? Oh, right. Sum mute n cloned. Primes. Fn self. Is prime of ref self. Oh, that's not what I want. Yeah, the thing is, so is prime is not telling whether the iterator is prime. It wants to tell whether a candidate is prime, but I want it to have access to the known primes as it goes. Is prime. All right, we'll do it. We'll say n 64. Cool. Tude. Fine. Right. So yeah, it's kind of an interesting thing. We can say in absolute terms is a number prime. But within the context of having objects in our program, we can really only say, is it prime relative to this set of known numbers? Because we don't actually have a reified set of all the primes. Okay, so what we'll do is we'll say for p in self dot, I guess for prime, for known prime in self dot known. Say p, as long as we're having n, we'll have p. For p in self dot, for prime and self dot known. How about that? Expected bool, cool. And at the bottom of this, we'll say true because we're in bail with false. Oh no, there's like a find if, right? So we'll say, oh, there's any. We saw there's any. Self dot known dot any. It's none of though. So is there? Let's take a look at iterator. Yeah, there's all, there's any. Is there none? Or do we just say not any? None of, maybe. I think in C++ it's called none of. That works well. Yeah, I think we're going to do not any. Oh, we could do all not. It's kind of the Morgan law here. We'll say all p n p is not equal to 0. That's a weird way to think of it. I want to think of this as not any of the primes divide n evenly. Yeah, there we go. Method not found in vacu64. Oh, because we need an iterator. Fine, cool. Right. If not, if let some blah, 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 blah. We'll say n plus equals 2. Kind of want to do while loop here. You can kind of fake one by saying it's a little Rust trick. While like that was equal to not self is prime. It would have also been nice. I know it's out of fashion to have assignments be expressions that have values, but this would have been nice. Okay. While n plus equal to 2, not self dot is prime n. So we are going to debug assert. I want to do a debug assert to distinguish from an assertion that's meant to catch an. That's not supposed to be in a test. It's not supposed to be verifying, validating input. I just want to demonstrate to somebody reading the code that I believe this to be true. So that is that n, so 2, is not equal to 0. We ensure that the last element of known, the last known prime is always odd. This lets us, when we add 2, we also add 3. We append 2, we also append 3 in the else case below. This lets us increment our potential prime n by 2 instead of 1 at a time. Okay. So why now? What's failing here? Oh, not yet implemented. Where do we still have it to do? Oh, here, Euler 7. We don't know this yet. Let's run it. Cargo cargo run 7 3. Well, that's not right. What is the 10,001st prime number? Oh, because we never added it. We need to say, okay, so now we found a prime number known dot push n. Let's try that again. Self dot known. Ooh, that was a little slow. 104,000. Does that sound right? So if we're looking for the 10,000, 1 in 10 is prime? That seems unlikely. Let's try it. No. 6th prime is 13. Oh, let's try that as a test case, actually. It's nice that they give us these examples. Let's make for nice test cases. Should we test Euler 7? We've been consistent about that? Test. No, Euler 1 we weren't. That's all right. Maybe I'll go back and change that at some point. In fact, yeah, let's do that. Source bin, Euler 1. Test, Euler 1. Rename a test function for consistency. Okay. Let's see, we'll have test primes. Let's give this thing a comment too. An iterator over the prime numbers. Oh, because we never returned 2. We never returned 2. Yeah. So this is going to be, I push n, and sum n is the final value. Else if it's empty, yeah, this isn't going to work. We need to keep track of whether we have returned the 3. So let's try this. So maybe we'll push one at a time. So let's match self dot known dot last dot cloned. We'll say if it's sum 3, then we get to do all of this. And actually now we don't need this comment or this stuff. If it's sum 2, then we just need to push 3. We know that 3 is the next one. Self.known.push 3. And if it's none, oh, it could be some other value, though. Yeah, this is if it's some other value. We want sum 2, some other value, and none. I don't like this ordering. In that case, we do the self-known.push 2. Yeah, this is mute n. Because there's no ordering. The order of these is neither the order in which we're going to push the values, nor the order in which, nor the reverse of that order. Self.known.last.cloned. Does that fix the bug? 4759. 4759. Nope. Let's see. Oh, we still haven't written our little test primes function. That'll help. But first, I just want to neaten this up. I want this to be in an order that makes sense. I'm going to match none first, even though we don't usually. Usually, we put these in the order in which the enum is defined. None. Otherwise, sum 2 push 3. Sum mute n while n plus equals 2 and not is prime. We're just going to n plus equals 2. No. Dot push n. Good. Looks right. Let's see. Test primes. Prime should be inexhaustible. What are they asking for? They're asking for, yeah, nth prime. So we want nth prime. Actually, let's just give primes an nth method. Well, it has an nth method. Yeah, the problem with the existing nth method is that it returns an option, because that's how iterators work. So we'll make a separate top-level function. Here. Nth prime 64. 64. We'll say, yeah, this. Prime's new, nth n, expect, and then Euler 7 just becomes nth prime 10,001. So then we have test primes is going to be assert equal nth prime. They said the sixth prime is 13. 6, 13. Does that pass? Expected use size. Oh, right. Should be a use size. Nope, that's a bug. Oh, because this should be 5. This should be... Yeah, then that passes. Yeah, nth is a little bit of a lie, because we call the first one 0. Nth, we call it nth, but it really takes an index. It's very subtle, the difference between ordinals and cardinals. So Euler 7 is going to be nth prime of 10,000. I think. So now let's run this. 104,743. Is that the one we had before? 104,743. What's a confirmation code? Okay. Okay, yeah, there we go. Off by 1. All right. 104,743. 104,743. I don't like not using the underscores consistently. Get rid of it here. Well, that's how they wrote it. That's fine. Run the test. I'm surprised, though, at how slow that still is. Okay. Solve problem 7. Let's run Clippy. See what... oh, Clippy's not unhappy. Clippy's in a good mood today. Clippy has smiled upon us. Oh, not 800. Why is it doing that? There. Oh, hey. The 4 adjacent digits in the 1,000-digit number that have the greatest product are 9989. Okay. Oh, so presumably 9999 never happens to occur. The 1,000-digit number, meaning this particular 1,000-digit number. Find the 13 adjacent digits in the 1,000-digit number that have the greatest product. What is the value of this product? Oh, so we're going to have to scan it. Yeah, this is linear. This is going to be like an order n thing. I wonder why they want these confirmation codes all of a sudden. Probably I loaded 2 problems too fast. Okay. Is that in fact 1,000? That is 50 per line. 20 lines. Yeah, that's 1,000 digits. All right, cool. Copy var Euler yada to source bin Euler 8. Euler 8. Let's statement. This should probably be indented as a code block. All right. Well, this is the number. Okay. So we're going to represent it as a string, clearly. Or should we have a, we should actually do, this can be a static string, right? We can have a const static. Is that how that goes? Const static? Digits, fine, equal, colon ref stir equals that. The rest is a little tricky about how to define const static strs. I mean, don't get me wrong, most languages won't really even let you do this. We could just make this a variable if we wanted to, a not const variable. And we want this to be, I want it to not have new lines. Will Rust combine adjacent strings? The way that some languages will, like C and C++, and I think Python. Okay. Expected identifier. Static, is it static const? Do I have to do it in that order? Expected identifier. Oh, there we go, const. Help, add semicolon here. 29. Nope. Looks like it won't do that. Well, that's a shame. There's got to be some way to combine these. Plus signs? Let me do that in a const initializer? Oh, maybe. Oh, it doesn't like those parentheses, though. Cargo, check. Cannot be used to concatenate two yada yada strings. Yeah, unsurprising. Without them, it won't concatenate them implicitly? Is it like a literal? Rust, concat, string, literals. Aha! If you literally have string literals. Well played, Huan. Concat. Oh, and that gives me my parentheses too. There we go. Could not compile. Expected token, comma. Oh, they need commas though. Fine. Digits is never used. Yeah, that's okay. Help, convert the identifier to uppercase. Oh, yeah. Oh, that's a compile time warning, huh, now? All right. Just never used. Fine. So, we need a substring, the highest product. So we can do we could scan through these. Oh, yeah, actually, let's scan through them. So let's say highest product. Digits. U size. U64. So we want to go for, we're going to start at the beginning. That's the first index at which we'll start scanning. Up until the last index at which we'll start doing it is, right, the length is digits dot len minus Num digits. Oh yeah, num digits could be a little bit confusing. It's more like the digits are a haystack and this is the needle. Nice product. Len? Should we just call it Len? Yeah, we'll call it Len. I don't love it, but again, if you have better ideas for the name, please do leave a comment. Okay, so for each of these, we could get really clever. Instead of taking the product of the whole sequence, we could divide by the one that's rolling out to the left and then multiply by the one to the right. Should we try that? It means I'm not going to get to do it as a filter here. It's going to get confusing. We could scan. Yeah, do we want loops in mutable state? That might be more efficient. Well, it entails division. All right, so let's just do this. So we'll say dot map some index digits at I up to, but not including I plus len. That's not a function. Dot product. Oh no, these digits are characters. We need to parse them. Digits. Okay, so let digits equal digits dot map. In fact, let's make this a vector of make them U64s just because the product might get large. Dot map digits dot chars dot map c dot parse. Will that do the right thing? Is that smart enough? What are we on? We're on 8. Method not found in char. Rust parse char as int. 1 becomes 1. 2-digit. 2-digit. Base 10. Map dot collect. Map's another example of an iterator that's not called iterator. I like this way better anyway. It's redundant to have iterators. Expect U64 found plot. Yeah, okay, fine. So that works though. We'll say we'll do the loop. Let mute product equal. No, we'll do the filter. Digits, or the map rather. Dot map. I had it here. 0, 2, digits dot length. Minus len. Map I. Now we can do this. I plus len. Dot product. And then we just want the max value. Yeah, this could fail. When would this be an empty? This would be empty if the length we were given was more than 1,000. More than the length of our given digits. So let's just say that in that case, unwrap or 1, because we have a multiplicative identity. Okay, collect can be built from other U32s. 2-digit gives you U32s. How do you like that? As U64. Product is not an iterator. Huh. I wonder if we'll ever get product on slices. Is that going to give me references? As expression can only be used to convert between primitive types or to converse to a specific trait object. That's what I'm doing, man. Oh, a CA reference? Is that what's going on? Expected char found reference. No. Char, 2-digit. Should be giving me a U32. Oh, option. Oh, it might not be a digit. All right. Okay. So they want this to be flat map. Is there flat map on these iterators? 2-digit flat map. D as U64. There we go. Warn dead code. Highest product is never used. So we want to test highest product. Let's test highest product. Highest product. Let's make this test Euler 8. Why didn't that must not be coming out of my template. Let's see, test. Yeah, we'll make this test Euler. Okay. Test Euler 8, yeah, not to do. We want that to be 99895832. So if it's 4 is what was it? 5832. 5832. And that passes. Good. So now we want, well, there's going to be highest product of how many? 13. Let's run it. Run Euler 8. Ooh, big number. Is that a 1? That's supposed to be 17971. Hey, all right. You are the bajillionth person to have solved this problem. Whoopity-doo. Yeah, both tests pass. Good. Yeah, I don't feel great about all the redundant arithmetic. Basically, this has become, instead of what should be an order n problem, where n is the number of digits, we now have order m times n, where m is this length. Because we're recomputing the, after we do this product, we're then going to do that product, whatever the one digit past is. We're going to end up multiplying 6 times 3 for every subsequence that includes those 2 consecutive digits. So there's definitely a more efficient implementation to be had. But this will do. It's always a judgment call. When do you stop optimizing? Solve problem 8. Push. Problem 9. Okay, and again they want the confirmation code. Pythagorean triplet is a set of 3 natural numbers, of which a squared, b squared, c squared. For example, 3 squared plus 4 squared is 5 squared. There exists exactly one Pythagorean triplet for which a plus b plus c equals 1,000. Find the product, ABC. ABC is Euler 9, source bin, Euler 9.rs. Yeah, these should be squared. What was it? It was B2, right? Cool. And bless you, Vim. We can ... Is that... Oh, they want this to be a whole block. For example, 32 plus... Is it annoying to be going back and forth like this? Leave a comment with that, too. Maybe we'll stop doing that. Yeah. For exists exactly for which a plus b plus c equals 1,000, find the product ABC. Cool. These are all also squared. Control V, U, B. Oops. R, Control V, U, B2, escape. Good. Equals 5 squared. Okay. That looks right. Okay. So what are we doing here? We need a Pythagorean triplet. Well, obviously the numbers are not bigger than 1,000. So we have a billion possibilities here. A could be any of the 1,000 numbers. B could be, oh no, they have to be A less than B less than C. Okay, so it's still basically cubic. All right. Yeah, it'd be nice if we could find the 3, 4, 5 one. Which A plus B plus C equals 1,000. I'll just brute force this. For I in, I'll start with 0, let's say. Up to 1,000, say. For J, for K, this has to be at least bigger than I plus 1. This will be J plus 1. Oops, gotta match those closing braces. If I times I plus J times J plus K times K equals 1,000, return I times J times K. And if we get here, panic, failed to find solution. Okay, let's try our tests with number 9. Number 9 fails. Of course it fails, because we don't know what the answer is. Let's see. What's test for? It's just been Euler 9. 0. Well, that ain't right. Why would it return 0? Oh, A plus B plus C. Oh, yeah. Okay, so sorry, we need to say, so if I squared plus J squared equals K squared, and I plus J plus K equals 1,000. Oh, that's slow. All right, let's try. Is this the answer? Oh, yeah, there's zeros in the end because we got lots of 2s and 5s as factors in there. 2, 5, 3, 2, 8. Okay, that's it. Yeah, I don't feel great about this code. Yeah, if they start making this like a variable number of terms, this is going to have to become something a little fancier. But for now, okay. Yeah, good. Solve problem 9. Let's do problem 10. The sum of the primes below, yabbity dabbity. Bar Euler source spin Euler 10.rs. Below the sum of all the primes below 2 million. Okay, right on. So yeah, now we definitely want our prime iterator. So let's move it into some library code. Which one had that? Primes. Euler 7. 7.rs. Let's make lib.rs. Euler 7.rs. Primes. Yeah, I think nth prime can go in the line. library code. So this will be pub struct primes. We'll need pub nth prime. Pub new. And is prime is not public. Okay. Now how do I import that? That's not going to work, right? 7. And prime not found in this scope. Bin Euler 7.rs. Use crate? But they're different translation units, right? It's technically a different crate. What is this whole thing called? This Rust Euler. Is it use Rust Euler? Colon, nth prime. Oh, there. It's right there. God, sometimes Rust and Cargo both are incredibly awesome. And I don't even think to look for it because I've been so broken by other tech stacks. There we go. All right, right on. And Euler 10. It's going to be the same code, basically. Use Rust Euler nth prime. Oh, no, we don't need nth prime. We need primes. It's prime time. We need sum of all the primes below 2 million. Let's make just sum primes below. I'll call it limit at this point because I don't want it to be mistaken for a count. You can call it value. I think limit's good. U64. Right, because they're not asking for a use, so they're not asking for a count. This will be U64. We'll say primes dot take while and p is less than. Ooh, are they inclusive? That doesn't matter for these. Limit. So we'll just say exclusive. Take while dot sum. Let's make this Euler 10 now. Not dot take while. Scope resolution operator take while. An argument of primes is missing. Oh, new. Expected because, yeah. Dead code, fine. So now we need, let's have test some primes below. Test some primes below. What we will do is we will assert equal some primes below, what was it, 10 should be 17. Missing token macro arguments. What am I missing? Oh, assert equal, duh. Okay, and that passes. Yeah, look at that F and the dot. Just, they were wiggling back and forth. Like this dash test threads equal 1. Very good, I think. So now Euler should be some primes below. What do they want? 1 million? 2 million. 2 million. 2,000,000. Where is it seen at you? Found cargo run dash bin Euler 10. Oh, is it just slow? Yeah, may need a faster way to find some primes. Do we need like a logging crate now to do conditional logging? Rust log conditionally. I'd love to not add any crates outside the standard library. Boy, I wish Rust had like a set of quasi-approved crates like Golang X that would be deliberately minimal and not just depend on arbitrary things from crates.io. wouldn't usually recompile your application. There's no you can pass environment variable. Yeah, that's probably the way to go. But it should be a macro. So that we only assemble the logging statements. Wow, that thing is really going. It's killing one core. That's another way we can go. We can start multi-threading. At least we have threads in the Rust native library. Possibly, we should pre-compute a ton of primes. Yeah. That may be the way to go. And then we'll just put them in a file that we just read in. Or that we link in, actually. It could be part of the library. Let's do that. Let's say, as much as I don't love code gen, what's the right place to put generated code? Rust, where to put generated code. There are build scripts I've seen before, but I think they're mainly meant for building existing code in other languages so you can link against it. That's not what I'm looking for. Generated build time, the correct way to do this via build.rs build script. Yeah, I had a really bad experience trying to get these things to work, to do some simple setup. Here's on a single card. Yeah, I might just commit it, as much as I hate maintaining generated code. And put a comment in it saying this was generated by, include concat and out there. Yeah, or maybe not even make it a Rust file. Well, this is going to be a big file. So if we're talking about 2 million primes, and they're more than a byte a piece, this is going to be multiple megabytes. Is there a faster way? Let's see. Fastest way to generate primes. Prime sieves, that's probably what we're doing. Still faster, but more complicated, and various wheel sieves are most common. Oof. Yeah, marking as composite all the multiples of a prime. To do so, it starts with something there. It's like because it starts with 2 as a black image on a transparent background for some reason as the first prime and marks all of its multiples 4, 6, 8. Then it marks the next unmarked number. That's not quite what we're doing. The same operation of crossing out the composite numbers, however, it does that with a different formula. Okay. So we didn't do any of these. 60. As the 7 to 3 subsets. After that, using each subset, it marks. Oh, jeez. The first 2 million primes, huh? I wonder what prime we're up to. You try to improve some constant factors here, but I don't think that's the way to go. I also wonder how much memory this is taking. I bet you can get a pretty good estimate of what number this is on based on how much memory it's using. Like none. This thing isn't using very much memory. We don't have an infinite loop somewhere, do we? I can start to hear the fans going. Should have timed it. Okay. It's Euler 9.rs. Nope, we did that. This is Euler 10. All the primes below 2 million. Oh, so primes below is take while, then dot sum. That seems very reasonable. But I think we're going to have to either pre-generate a bunch of primes and let this thing run for a while and just have a huge file. We're going to need a better algorithm. While we're at it. Oh, there we go. How long did that take? I think this thing should be pretty well convinced I'm human by the fact that that took forever to run. There's got to be a better algorithm than that. I am kind of curious, so I'm going to let this go also in the background. I'm going to make a new tmux window here and just say, oops, not that. I want time cargo run dash dash. Oh, you know what else I didn't do? I'm an idiot. Cargo build dash dash release. Oh, that's not what I meant. I want to run just this one. Dash dash release dash dash bin. There we go. Yeah, so it's not like checking for overflow. Let's see how long that takes. Honestly, I think the build time, the cargo time is negligible. Here, I'll do it. Yeah, in another tmux window, I'm going to say, oh yeah, we're still down in the target directory. Time. Target. Release. Because at some point I want to be able to mark off slow tests. Euler. Okay, I built them all release. All right, so let that go. I'm not too worried about the other load on the machine either. This thing is single threaded. I'm not nailing all the other cores. Okay. What did I do in Euler 7? Oh, I moved it out. That's right. This is now library code. Git add lib.rs. Git add bin Euler 7.rs. Cargo test dash bin Euler 7. Oh yeah, it's a little slow. All right, we'll see if that becomes an issue going forward. Factor prime number generation into library. Great. Into libcrate. Move prime number generation to libcrate. And then solve problem 10. Okay. Oh, this took 26 seconds in release mode. Yeah, it took longer because I was doing it in debug. Is that still the right answer? 1429, whatever it was. Oh, they'll tell me now, right? If I reload this. Yeah, 1429, something 22. Looks good. So, for the test, do we want to disable the test as being slow? I think we do, because if we say cargo test right now, it's just going to take forever. I'm willing to tolerate the slow-ish ones, but I don't have to build in release mode anyway for running tests. So let's say config. If we break it, this smaller one will probably catch it. I'm glad we have that. Yeah, this needs to be that value. We're going to say config slow tests. Let's see, rust arc slow tests. 2015. Probably still valid. I don't want not feature equal expensive tests. Look at that. Configure after. Test dash ignored. So including all tests marked with #ignore. Really? So can we also just do slow? You say slow. Cargo test. Cannot compile. Cannot find attribute slow in this scope. Yeah. Well, unless ignore is special. Ignore. It is. It'd be nice to. Oh, dash ignored. Yeah, but we ignore tests for different reasons. Sometimes there are tests I don't expect to pass, and then there are tests I expect to pass eventually. And this is the latter. So let's say, what was it? Example in the, yeah, let's see how this is doing. This is on a particular commit. Let's look at the current version of this code. Oh, it's in num. Whoops, which isn't even in the standard library anymore. Crates.io. Num. Although, I guess you still use an ignore. Repository. Rust num. Let's search in here. We want ignore this repository. Couldn't find it. Yeah, that's not even that anymore. Slow. Expensive. No, bad example. All right, I think this is what we're doing. Feature flag config after. If not, feature equals expensive test. Well, that's my feature. Slow. Yeah, it's just always there. I don't know why it tells you 0 ignored by default. Expensive test doesn't. I guess that's the level of support they offer unless you want to get very fancy. So all right, I think that's it. Takes tens of seconds even in release mode. I'll make it. This test takes tens of seconds to complete, even in release mode. All right, so if we say dash ignore, say time cargo test dash release dash bin Euler 10. Yep, good. And if we say dash ignored, what did we do a second ago? This person had dash. Of course dash. Why wouldn't it be dash? There we go. Oh, it runs only the ignored tests when you do that. This is going to take 26 seconds, right? All right, well, on that note, we'll just wait for this to finish. And then I will probably take a break before we go on to number 11. Yep, sure enough. 25 seconds and change. All right, well, thank you for being with me through problem 10. I look forward to, let's commit this. Ignore slow test by default to run it. Pass cargo test dash call cargo test dash release. What did we just do? Whatever the thing is that just worked. Run it. test anyway. You may run the slow test anyway, thus. All right, good. Push. All right, let's take a break. I'll see you soon.